And we're on our way into London today by a high-speed train. And I'm going to be meeting up with Mikael Holmberg, and we're going to be talking about the fantastic subject of time, and specifically PTP, Precision Time Protocol. Come join me on this trip. I'm here with Mikael Holmberg. Holmberg, is that right?
Yes.
Holmberg.
Yeah.
Well, welcome to London.
Thank you, Isaac. Nice to meet you here.
And
in
welcome,
Greenwich.
And welcome to Greenwich.
Yeah.
Greenwich.
Yeah.
Greenwich.
Greenwich.
Yeah.
Greenwich.
The center of the universe. This is where the British invented time.
Okay, so we are going to talk about time today, right?
That's exactly what we're going to be doing. 2002 was the first protocol.
2008.
2008 was the first. What was wrong with the first protocol that they needed to bring in the second one? I know for one, it only had IPv4, right?
Yeah, that's correct. Yeah, I think the 2008 was kind of the introduction to that one, and that was mainly for the telco space at that given time, you know, for the cell tower synchronization.
Who was it just the IEEE as a standards body, or was it the Ericssons, the Nokias, those
Yeah, I think it was the standards committee, the IEEE. Obviously, you have all the telco, you know, equipment providers. The telcos were in driving that as well to get it into a standards-based thing.
So the telcos were fundamental. They needed PTP, right?
They needed PTP,
because without PTP, you couldn't do that type of scale.
True, because of the fact that Ethernet was seen as the transport media where PTP was, you know, needed.
Understood.
Yeah.
Okay. So Michael, when I came in today from Cambridge, I came in using a train, right?
Yeah.
And timing is so important there, because when you look up at the timetable, you've got to, you know, timing is important for there, right?
Yeah.
So it's got to arrive, and you can't have one station, you know, being 5 minutes offset from another station. I mean, that doesn't make sense. So time, even in something like public transport, buses, trains, things like that, it's got to be accurate, right?
Correct.
And number one, because you want to get to your destination on time. So
Yeah.
that's really important. But the other thing, of course, is you don't want accidents, right? If you didn't have that type of time synchronization, what is 10:30? It could be different things if
depending on where you are.
Exactly.
Yeah.
So this protocol that we're going to be talking about, and generally timing on networks, on electronics and stuff, it really is important. It really plays a massive part, even if we don't consciously aware of it. If you think about 200-300 years ago, when the first railways were being built across the UK, across America, places like that.
Yeah.
They must have had these issues where they had to start thinking at that time already about like if you got a train going from New York to Texas or whatever it was, I don't really know, but you would have had to have a system of synchronization between them so that you know, and that you don't put two trains, you know, onto the same track, etc. So this is not new stuff. This has been issues that we've been dealing with learning for ages, right?
Yeah.
And it's more than just seconds. We are not talking just about seconds. It's now milliseconds and it's nanoseconds, right?
Exactly, and I mean, spot on. We talk about, you know, the accuracy of hundreds of nanoseconds. I mean, imagine the accuracy that is needed for getting into, you know, such figures.
Yeah. By the way, nanoseconds is a billionth, right? 90.
Yeah.
1 billionth of a second. A billionth of a second. It's like, you can't even really imagine it.
No.
I heard a good description by an admiral a while ago on the internet and on YouTube, and she said, how far is a billionth of a second?
Yeah.
Which kind of felt like a weird question, like how far is a billionth of a second? And it turns out that a billionth of a second is about a foot long, right? It's about, you know, how far light can travel in a billionth of a second. So it's about that much, you know.
True, it's pretty interesting because, I mean, as such, it's quite abstract, right? But when you put it into some context like that, it kind of tells the story.
Yeah. Michael, you and I, we've been around computers for a long time, right?
Yeah, for quite a while.
I mean, I still have.
I don't have any hair anymore, so you know. We've been around here for quite a while, as you said.
But you know, I've been around from the days of DOS, right?
Yeah,
I don't know if you remember. Do you remember DOS?
I do remember DOS.
And Windows, the first version of Windows, and Windows 3.1, and then network in Windows 3.11. But at that point in time, right, you already needed time on your computer, right? Every computer had a little battery and all of that. What has been the driver for the change in time? You know, what we had 30, 40 years ago is no longer good enough for today. What was it that's changed? I guess operating systems, applications, all of that has driven the need for change in time?
Correct. And as I kind of alluded to earlier on, obviously telcos were more or less setting the stage for the need of time synchronization, but starting to look today at applications, at use cases, you know, where synchronization of time is becoming critical. And as you know, we have NTP, or we used to have NTP. Obviously NTP is still around, but the accuracy of NTP is not enough. Hence you need to start to look at something else that would truly be applicable for, you know, coping with as we discussed, you know, the hundreds of nanoseconds accuracy on synchronizing time.
So applications, I guess today, you mentioned telcos. I guess the introduction of mobile networks around the world, that must have been a big driver to have really accurate time, because we were not talking about, you know, 10 users on a network of 1,000. We're talking now about millions of users on a network, right? So that must have been a big driver for that. And I guess years later, things like you know, social media. That must have, you know, you got clients like Meta today. 2 billion, you know, customers on their networks, right? It's a serious amount of users. It's huge applications.
That's true, and it's interesting that you mentioned that one, because Meta is a good example. I mean, they use PTP to synchronize database transactions. And if you now imagine you have huge clusters, you know, database clusters, in some way you actually need to synchronize any transaction that you know the exact time when that transaction happened. So that's a good use case. You start to see this coming into play in you know, the audio video, the professional audio video vertical. You start to see this coming into place in industry. You have manufacturing, you have, you know, site plants, you have a different, you know, kind of use cases, applications.
Scientific. I mean,
scientific as well.
I have a friend who works at CERN, and there you know, timing is everything, right? You've got atoms smashing into each other at incredible speeds, and the data that is gleaned from that needs this type of precision, right? If you're going to discover things like the Higgs boson and stuff like that, timing is absolutely key. You know, you don't ever think you'd need a billionth of a second, but actually there's probably many applications when you do.
And the funny thing is, I mean, we know Ethernet, right? So Ethernet is a 50 years old technology. And obviously Ethernet has changed over time. And now you are going into moving or Ethernet becoming a more kind of deterministic technology. And obviously timing and synchronization of timing is becoming key for that given, you know, Ethernet evolution phase as well. Due to new use cases, due to, I said, Ethernet ubiquitous, you have basically a huge ecosystem, so why not?
It's cheap, right? So it's really cheap, and people know it. I mean, exactly. You don't have to be a professor or a distinguished engineer to understand Ethernet, right? It's just like you go anywhere in the world. Ethernet is Ethernet. That's standard. TCP is TCP/IP. If you understand that, you understand. So, so these proprietary technologies, they ultimately fall away as more and more applications come over to Ethernet, which you mentioned AVB. Haida, our colleague over here, is filming us. I want to film him a little bit later because he was a sound engineer at a West End theatre for many years. And he has, in fact, that was one of the first ways he knew about extreme networks, because we support the AVB protocols, right? Audio video bridging, where their technology as well, in the past, they just used to have these long, they call them snakes, these cables, you know, every microphone on stage, everything going through its individual cable. And now that whole industry has been able to change and transform and start using standard Ethernet, right? True. But timing for them has been massively important. The timing, the voice, the video, the lighting, all of that synchronization is now totally, it's Ethernet, but totally dependent on accurate time.
True.
PTP.
And that goes back to what we discussed.
Sorry, I keep saying
Ethernet is
PT, it's a precision time protocol, PTP.
Correct. PTP, So that basically goes back to what we mentioned, that, you know, Ethernet is ubiquitous, and you basically need to figure out ways of dealing with you know, time and synchronization of time with such technologies because of the price factor, because of simplicity, all those different things.
This is a very interesting place. I think many people who come to London might not know about Greenwich, but in some way or other, most people have at some point come across the term, because when you're talking about time zones, if you set up a Zoom meeting or whatever it is, it always asks you, the location where you are based or something like that. And it'll either be like London, it'll say UK, London, and then in bracket it would often say GMT.
Plus or minus something,
Greenwich Mean Time. This
That's
is the significant. So we are in a really significant place, not just in the UK, but in the world of time. This is really important. And we're going to go up to the Royal Observatory just now, and I'm going to show you the meridian, zero meridian. So if you think of the world as an orange, as a sphere, 360 degrees, right? If we were to split that up, say into 24 slices, an hour each, So imagine an orange split up into these 24 slices, and then each one of these slices would be like 15 degrees. That would make 360. But slice 0 is up there.
So we are basically close to slice 0.
We are basically on slice 0, and this is really significant because there was a real urgent need. Not only today, we're talking about precision time, but in hundreds of years ago, navigating, understanding the stars, how to find your position, all of that depended on time. And this is the significant place. So I'm really happy that you came and that I can bring you here to Greenwich, and we'll go up to the meridian. You can actually stand with 1 foot on 2 slices. It's a special place.
There you go.
Right. So now I am talking to you, and this signal is bouncing, I don't know, around the world or whatever it is. Is this working because the clocks are synced? Is that why this call is able to happen?
Correct, and as you can clearly hear, the voice. It's crisp, it's clear. If we weren't synchronized, if the base stations we are actually connecting into weren't synchronized, then we couldn't actually have this call due to the fact that it would be like you would hear something every now and then. So it's a matter of the frame, being truly not drifting, so to speak. And you need to synchronize, obviously, the base stations we do connect to now with these 2 handhelds. They need to be synchronized.
So the base station that's providing the signal to you and the base station that's providing the signal to me. So even though we're standing close to each other, those could be 2 very different base stations, because you might be Vodafone and I'm on another network over here. So we could be connected. If those were not synced, we would...
Exactly. That's what you would eventually hear.
That's how it would...
And then your call will be disconnected.
Okay. And I guess voice is just data, right? It's voice over IP. That would be exactly the same thing for all our social media, right? If the clocks were not synced, we wouldn't be getting the Instagrams, the LinkedIns. That just wouldn't happen in that way. We would have issues with that.
True.
So Michael, NTP, right? Network Time Protocol, right?
Yes.
It's been around for ages.
It has.
I remember at one of my previous companies buying like an atomic clock kind of radio, with an antenna on the roof and things to synchronize the time, within our infrastructure, right? So by the way, NTP was really about synchronizing hardware devices, right? Appliances, whereas PTP, we'll talk about it just now, is more on the data plane, right?
Correct.
But what is it that NTP doesn't give us?
So I think we kind of touched on it earlier on, but the fact is that NTP is, microseconds levels, while PTP goes into, as we previously discussed, hundreds of nanoseconds. And I think to put that into some context, why NTP is not enough anymore. Pick, for instance, the kind of well-known use case that is spoken about in regards to 5G and autonomous cars.
Latency. You need very low latency. Right?
And you talk about something called the URLLC, which is the ultra reliable low latency connectivity, which basically means that imagine you have a car which is autonomously driven. you can't actually afford to have a car stopping in 1 meter when it's supposed to stop in 5 centimeters.
So it's the difference between life and death.
Correct. And guess what? That's due to latency on more or less the communication path. And that's where you basically then go into the fact that you need to have a mechanism in place that actually would give you that accuracy on the level of hundreds of nanoseconds instead of microseconds. Hence, NTP is not applicable.
Things like Starlink, right? If you got this conglomerate of satellites that are feeding internet down, they could synchronize all autonomous cars, right? So that all autonomous cars are aware of each other, and they are all synced according to PTP. Correct. Right? They all synced on that level.
Yeah, and you can expand on the use cases. You get into industry, right? You have your manufacturing floors where you need to have the robots in sync. You go into a wide variety of different, use cases and verticals where that becomes applicable, where it's truly key to have low latency connectivity.
So traditionally speaking, network language, IT language has often used phrases like master and slave. And in PTP, it's exactly the same. If you look at the documentation, official documentation, that is kind of the language that is used. This is 2024, and times have kind of changed. So we're going to use other language. We'll use primary and secondary. It's a good term. It implies exactly the same thing. And you can relate that however you want to the technical documentation. Explain to us in a simple language how this protocol actually, works. It's kind of event-driven. It's kind of like almost like a handshake kind of thing.
Correct. It's like a event message exchange between two entities, being the
primary,
and
then the secondary, if you want to call it.
Somebody who basically consumes that or adjusts, the timing based on that event message exchange.
So I'm the primary clock, right? Yep. I'm the primary clock. I look at my timestamp and I say, okay, it's exactly midday, 00000.
Yep.
And that's an event message that I send to you.
To me, yeah.
Right.
And that's
so let's call that T1.
That's
right.
T1.
Time one. I send that to you.
Yeah.
Then I send a follow-up message just saying I sent it.
No. So you send the T1. I acknowledge that with a T2.
Ah, okay. Yeah. So you receive that.
Yes.
And you acknowledge that you've received that with a T2.
Correct.
Okay.
And then you send a T3 again.
So then I send you but when you acknowledge, you tell me the time that you received that.
Yeah.
Okay, so I sent it, let's say, at 12 o'clock 000. You received it, let's say, at 12 o'clock 001, for example.
Yeah.
You send that back to me. I send you another packet, and I say, I'm sending this to you at 12:002.
Yeah.
Yeah.
And that's a follow-up. Yeah, that's a follow-up. Yeah.
And then you send me T4, which is an acknowledgement of when you received that.
Correct.
One. So now we have two different times. When you received it, when you received my first one, when you sent me your second one, when you received the third one, when you sent me the fourth one.
And I basically have those four.
So you have that those 4 bits of information on the secondary, all right. So now what happens is, now we do a calculation, right?
Yeah.
So now we put double brackets, single bracket, and we say T4 minus T3, right, in brackets, take away T2 minus T1, close brackets,
yes,
and then we divide it by those two times,
yes,
and we'll get a figure, and that figure is the offset, right?
Correct.
Between the time it takes from A to B, from the primary to the secondary, that's that offset, and then that secondary is going to adjust the time by
as the consumer of that is going to adjust based on that.
That's really simple.
At the end of the day, it's quite simple.
It's really simple.
Yeah.
So if you were doing that, if you were doing that on a constant basis, I don't know, every minute, 2 minutes, whatever it is, but or even less than that, every 10 seconds or whatever it is, it really means that if you got a big infrastructure, that it's very easy to keep all of those devices in absolute sync, right? Because they're all just adjusting for that little offset.
Agree. But I mean, as you mentioned, it's kind of simple when you put it into a nutshell as we do here now.
Yeah.
But there's a lot of things behind that when you go into the 1-step, 2-step clocking, all those different things. But
sure.
In a nutshell, I mean that kind of tells the principle.
The principle of that.
Yeah.
That's really clear. I think people can understand that. Haida, you've been in the AVB business, in the audio business. You ran audio for a West End theatre for many years, and that was incidentally how you heard about Extreme Networks, right?
That's right.
Because we had AVB. So tell me how AVB, audio video bridging, is used in theatres nowadays, what it's used for, and how PTP plays a role in that as well.
Okay, well, so when it comes to audio networks and video networks, timing is absolutely everything. Whether it's because you want to sync up video with audio and you want the lip sync to work, or whether it's because you've got multiple audio channels. If you think about recording a live orchestra, all those signals are coming in and they need to be in time. The orchestra is playing in time, so we need to be able to record that in time. So PTP and AVB TSN, they're foundations of that. What they do is they guarantee the time that those packets are going to arrive based on the timestamps. It's really important when you have things like, say, a line array. Line array is basically a stack of speakers all stacked together, acting as one speaker. Now, there's tiny little drivers in all of those boxes, and they all need to move as one. Now, if the packets are arriving at slightly different times, even if it's milliseconds, microseconds, that will throw the quality of the sound way off. If you want lights to flash in sync, you need to make sure that they are absolutely synchronized. So if you take a video of stage lights and they're flashing in sync, if you slow that video down, you'll actually see that maybe they're out of sync. But something like PTP, TSN will allow you to make sure that they're coming on and off exactly at the same time. So you're guaranteed that your video quality, when you're talking about LED lights in the video screens, whatever it might be, is as bang on and precise and accurate as it can be.
So let's talk about quickly our partner community, all right, and our salespeople.
Yeah.
What about PTP? What do they do if they have customers that are asking for PTP, for example? How do they approach it? What's the call to action? Do people contact you? Do they contact people? How do they go? What do they do?
Yeah, I think it's a key thing to understand that we have the foundation for PTP set in various platforms already. So the hardware is there basically. What we need is obviously add on the software features that, as we discussed, the profiles, various profiles, boundary clock, transparent clock, all those different things. So I would think that the way forward for the sales community is to truly, get in touch with the PLM and basically, go through the use cases if they have specific needs, use case-wise, so on and so forth. So we can just, collect all those cases and then start to look how we can actually map these to a possible roadmap.
Yeah, the more interest it is, the higher priority it becomes.
Exactly,
right?
exactly. Yeah.
Perfect.
Yeah.
Okay, well, you heard it there. Everything you needed to know about PTP, but we're afraid to ask. Hopefully this video helped to answer some of those questions. Michael, thank you very much for coming to talk to me about PTP, coming to talk to us. It was a total pleasure meeting you and having you talk about this. Really appreciate it.
Thank you for having me, and pleasure to meet you guys as well.
Thank you once again.
Thank you.
Cheers. Bye-bye.
Bye.